All right, guys, I want to dive into section 2.2 with you. And let's recall the definition of the derivative of a function at a point. So we get f prime of a is the limit as h goes to 0 of f of a plus h. Let me rewrite that. F of a plus h minus f of a all over h. And so this gives the slope of the tangent line to f at x equals a. That's what f prime is. It's a number and it's a slope. And so the key takeaway here that I want us to see today, let me slide this down and draw a picture for you, is we're going to switch notation just the tiniest little bit. So the way that we're thinking about this right now is I have a function, and maybe this is my function f, and here's my point a, and we're computing the slope, and we're calling that a, right? This is x equals a. But there's really no reason to label this arbitrary point a. We could just call it x. And let's do this and see what happens. So basically in this formula, I'm going to replace the a's with x. So now you pick your x, and we're going to compute the derivative at x. And so the new notation that we're going to use, let's just put it here, is f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And so this gives the slope of the tangent line to f at x. So same thing as this, slope of the tangent line to f, we'll just say at x. We don't need to say x equals a anymore. So I think this is best seen through an example, and then we'll hop on Mathematica after we compute this and try to visualize what's happening. So here's a function, f of x is x squared. We want to compute the derivative at an arbitrary point x, and so we're going to realize that f prime of x, which is the slope of the tangent line of f at x, this is the limit as h goes to 0 of f of x plus h minus f of x all over h. I'm just writing down the formula so you can see it. This is the same thing as the limit as h goes to 0 of, well, what does f do? F squares whatever you plug in. So you get out an x plus h squared minus x squared all over h. And so now let's carry this down here, and we're going to get the limit as h goes to 0. Now think about it. We've got to do more work because the form is 0 over 0. So the form of this limit is 0 over 0. So we're going to try and expand the top and then combine like terms. So I'm going to write this as x squared plus 2xh plus h squared minus x squared all over h. And this is the limit as h goes to 0. These cancel. And I don't want to do too much in any one step, so I'm going to go ahead and write the next step out. And now at this point, I can cancel an h. Be careful canceling h's. People often will cancel incorrectly. If you can cancel, you can factor. So I can factor an h out. That allows me to cancel. I'm actually going to write this the way that I would factor it first, just so you can see it. So just to be safe, I'm going to write this as h times 2x plus h all over h. And then I'm going to cancel those factors. And so I get the limit as h goes to 0 of 2x plus h. And now I want you to realize in all of these limits that we're working, the letters can be a little bit overwhelming for people. The x's and the h's and, what is going on. What I need you to realize is that as far as the limit is concerned, h is the variable and x is not. So in this limit, h is going to 0, h is in motion, x is static. Even though we're treating x as a variable, I want you to think of it as somehow not moving. It's not changing. It's just a constant. It's just along for the ride. So this is a polynomial in h. And so at this point you can just plug in h equals 0 and you get out 2x. And so I want to think about, let me slide this next example down. We're going to need more space. I want to think about the significance of this. So this is saying that at any x that you want, the slope of the tangent line of x squared is 2x. And so let's do this by hand for just a second, and then we're going to hop over to the computer. So let me graph just the roughest sketch of x squared. Here we go. And so, for example, I know that at 0, when x is 0, the slope of the tangent line is 2 times 0 is 0. You can see that, right? When x is 1, the slope of the tangent line, let's pretend this is 1, slope of the tangent line is 2. When x is 2, slope of the tangent line is 4. When x is 4, slope of the tangent line is 8. You can see those slopes getting steeper and steeper. And so let's switch our perspective now to Mathematica and see if that can help us.
So the top function is our x squared, f of x is x squared. The bottom function is the derivative, which is 2x. And I want you to realize that f prime equals 2x. That's a function. We get another function. And so we view the derivative as a number, but the derivative is actually, the way we've computed it is a function, and you plug in any x value up here. So for example, if I plug in, let's go to 0. If I go to x equals 0, I can see that my, can't quite line it up on 0. Ooh, there it is. That's close enough. Okay. You can see that when I'm near 0, the tangent line there has slope that's almost 0. And when you look down at my f prime is 2x, the formula is whatever x value you have, multiply it times 2. And so you can see that as I trace out the tangent line, this new function, 2x, gives me the slope. Look here, the slope is negative, right? Down here, the slope is negative. Slope of the tangent line is negative. When we slide the tangent line up a little bit, the slope is positive. And you can see the slope, the output of this function is positive. So this function, this line, is our f prime equals 2x. And you can plug in any x you want. You can plug in x equals 2. And when you see that, I actually am off the screen on the top graphic. That's okay. You can see that the output here is 4, and so the slope of this line is steep. And so I want you to see the connection between the slope of the yellow line and the y value of the derivative. That's what the derivative does. The y value is the slope of the yellow line at any given x point. You can see negative slope, negative slope, negative slope, negative values. All of a sudden, we're getting closer and closer to slope 0. There's slope 0 almost. And now the slope is positive and the derivative is positive, so on and so forth. So that's the connection. We're going to start viewing the derivative as a function, which when you want to get the actual slope of the tangent line at a certain point, you simply plug that point into the derivative function, and it spits out the slope of the tangent line that you want. So we'll do some more examples and try to help this make sense.